what we have seen here in this particular diagram, you can observe parallel in serial out type of shift register, and it consists of 4 D flip-flops and some additional logic for it. Okay, so all of you, can you see the screen? Tell me, can you see the screen?
Yes, ma'am.
Okay, so now here, as you can see, this shift and load control is used here. So it is used for deciding whether it is a loading operation or it is a shift operation. So we have seen that when this line is equal to 0, then we have observed that this upper line, it becomes 1, and this lower line, it is 0. Okay, so if this is the case, then what happens? In this case, one of the inputs of AND gate number 1 is 0, AND gate number 3 is also 0, and AND gate number 5 is also 0. So one of the inputs is 0, so whatever may be another input, its output will be 0. So output of AND gate number 1, AND gate number 3, and AND gate number 5, they are equal to 0. Now you can observe, as this line is 1 and this is connected to AND gate number 2. So one of the line of one of the input of AND gate number 2, AND gate number 4, and AND gate number 6, they are at logic 1. So if they are at logic 1, then its output will be equal to another input. Okay, so here you can observe B0 is applied to your first flip-flop. Okay, then B1 is applied. Here you can see B1 is applied. One minute, somebody is coming. So here what we have seen that as this line is 0, this will be 1, and this line will be 0. And as this line is 0, output of AND gate number 1 is 0, AND gate number 3 is 0, and AND gate number 5 is also 0. Okay, now if you observe this upper line, if it is 1, then we can observe here this is D0, and for D0 input is B0. Okay, and that for this D1 input is B1, because one of its input is at logic 1, another input is at B1. So 1 dot B1, it gives rise to B1. So 0 plus B1, it gives rise to B1. So input of the first flip-flop is B1. Input of the second flip-flop in this way, again it will be 1 and it will be B2. So here it will be B2. So 0 plus B2 again. Here you can see to D2, B2 input is applied. Similarly, if you consider this third flip-flop, then again you can observe this is 1, this is B3, this is B3, and this is also B3 then. So B3 input is applied at input of the flip-flop number 3. So now you can observe the inputs are present at the D input of each flip-flop. So this is your load mode. What it is? It is your load mode. So when this control line is equal to 0, you can load data. So apply data to B0, B1, B2, B3, apply a single clock pulse, then in that case, whole data is into parallelly loaded into your shift register. Okay. Now suppose here we are applying the data 1 0 1 0. Okay. So suppose we have parallelly applied data 1 0 1 0. So let us consider this. So what I have told you, when shift oblique load bar line is equal to 0, load operation is activated. The input data is parallelly loaded to your shift register. So each D input of the flip flop will get input. So B0, B1, B2, B3, they are parallelly inputted to the flip flop 0, 1, 2 and 3, and when you apply a single clock pulse, this clock pulse is simultaneously applied to all the D flip flops, and after application of the clock pulse, this input will be available at the output. So B0 will be there at Q0, B1 will be there at Q1, B2 will be there at Q2, B3 will be there at Q3. So in this way, with help of a single clock pulse, you can load data parallelly into the shift register. Okay, so this is loading operation. Now we should see how to shift this data through output, because here you can observe there is a single output which is denoted as Q3. So all the data must be outputted through this Q3. Okay, so how this happens, that we are going to see. Okay, so first of all I will clear all these drawings, and let us now see that when this shift oblique load bar line is at logic 1, what happens here, that is what we are going to see. So this lower line, it becomes 1, and upper line it becomes 0. So upper line is given as input to AND gate number 2, 4 and 6, and therefore one of the inputs of AND gate number 2, AND gate number 4 and AND gate number 6, they are all zeros. So whatever may be its another input, its output will be 0. So AND gate number 2 is having 0 output, AND gate number 4 is having 0 output, and AND gate number 6 is also having 0 output. Okay, now let us see what happens in case when this lower line is at logic 1. So when this lower line is at logic 1, you can see here this is applied as input to AND gate number 1, AND gate number 3 and AND gate number 5. So one of the inputs of AND gate number 1, AND gate number 3 and AND gate number 5, they are held at logic 1 level. So if this is the case, then what will happen is that inputs of AND gate number 1 will be 1 and Q0. So 1 into Q0, it will be Q0. Okay, and Q0 plus 0 is again Q0. Okay, so D1 will be equal to Q0. That means it is as if you have connected Q0 to D1. So you are connecting Q0 to D1 through this AND gate during the shift operation. Similarly, here you can observe the Q1 output will be connected to D2, because one of the input of AND gate number 3 is 1, another input is Q1. So output of AND gate number 3 is Q1, because 1 into Q1 is Q1, and now inputs to OR gate are 0 and Q1. So 0 plus Q1 is equal to Q1. So here you can see the Q1 is connected to D2. In similar way, here you can observe this Q2 is connected to D3. Okay, so in this way the connections are there. So I will draw this with some another color so that you'll come to know it is as if you are connecting through these gates to this input. Similarly, as if you are connecting this through this gate here. Similarly, with, it is as if we are connecting with simple wire Q2 to D3. So now these are your connections. Okay. And earlier what we have seen, we have loaded some data here. And that data was 1, 0, 1, 0. Okay. So at the first clock pulse, when you have loaded the data, the least significant bit is outputted at Q3. Least significant bit is outputted at Q3. So we have 0 at Q3. Okay. Now suppose if we apply one more clock pulse, then what is going to happen? So that is what we are going to see. So here, as you can see, this logic 1 is connected to D3. So now your D3 is at logic 1 and 0 is connected to D2. So D2 is at logic 0 and logic 1 will be connected here. Okay. And here B0 is there. So you don't care about this input now during the second clock pulse. Now suppose if we apply a second clock pulse, then what will happen? This 1 will be loaded to flip-flop number 1 because this 1 is given as input to D2 and therefore do not care about the output of Q3 at this time, but this now 1 will be shifted to Q1. So output of flip-flop number 1 will change from 0 to 1 because 1 is applied here. Now, as you can see earlier, 0 was present here and output of this will become 0 now. Here 1 was present, so it will become 1. Okay. So now the output of your shift register will be X101. X means what? Don't care, whatever it may be, don't look into that. Now the second bit will be outputted at Q3, which is 1. Okay. Now when we apply third clock pulse, here you can observe the output of flip-flop 0 you should not care about. The output of flip-flop 1 you should not care about. Okay. Now you can see here, what you can see is that I will use some another color so that you will understand it better. So let us use black color. Okay. So now what was our previous output of Q1? It was 1 and this one is now applied here. This one is applied here and previous output of Q2 was 0 and this 0 is applied here. So the present inputs of flip-flop number 2 and flip-flop number 3 are 1 and 0. And we are not caring about what are the inputs of flip-flop number 0 and flip-flop number 1. So this is what is case now. So we are applying the clock pulse. After application of the clock pulse, now this flip-flop has input equal to 1. So its output will become 1. Okay, so this flip-flop has input equal to 0. Its output will become 0. Okay, so now our output is XX10. So the actual serial output we are getting here is 0. So now 0 is outputted. So now only one input is remaining and let us see how that is shifted over here. Now in this case, as you can see, in next condition, we need not worry about flip-flop 0. We need not worry about flip-flop 1. And we also need not worry about flip-flop 2. Just what we have to see is about flip-flop number 3. Now here you can observe the previous state of flip-flop number 2 was 1, and this 1 is applied as input to your flip-flop number 3. So now input to flip-flop number 3 is 1. So when you apply a clock pulse, its output will also become 1. Okay. So now now output of the shift register will be X, X, X and 1. Okay. So now what is at the output Q3? 1 is present at output Q3. Okay. So here we have loaded whole data and we took 3 more clock pulses to output the remaining data. So in this way, this 1010 is outputted serially. So while outputting, LSB is outputted first and MSB is outputted last. So that is what you can observe here. Are you clear about this? Yes, tell me. Are you clear about this? If you have any doubt, you can ask me.
Yes, ma'am.
Are you clear? What you have to remember is when your control signal is at 0, there is parallel loading operation. When control signal is at 1, there will be shifting operation. Okay, during load operation, LSB is outputted, and during shift operation, remaining 3 bits are outputted. So that is what you have to remember. Now let us draw a truth table of this. Okay, so now I am going to share whiteboard with you. And let us draw a truth table of this flip-flop. Sorry, shift register. Shift oblique load, and this is load bar actually. Load, LOA, and load bar. Okay, and all these are outputs. So suppose this is Q0, this is Q1, and this is Q2, and this is Q3, and Q3 is your actual output. Q3 is your output. Now how this works? So when your shift and load is at 0 and you apply a clock pulse, then data will be loaded. For example, I have taken data to be equal to 1010. So data will be loaded into the shift register. At this time, LSB is outputted. So this is your output. Now, if I apply the first clock pulse here, then and make this shift oblique load bar equal to 1. This must be made 1. So if this is the case, the next state will be Q0 is X. Q0 is X. This will be 1. This will be 0. And this will be 1. That means now 1 is outputted. Okay. So apply second clock pulse here. Again, your shift and load control should be 1. Don't care about Q0. Don't care about Q1. And in this case, you can see 1 is there at the Q2 and 0 is there at the Q3. So 0 is outputted. during the third clock pulse. So, so here we are going to apply the fourth clock pulse. So again here shift oblique load bar must be equal to 1. So here you need not care about Q0, Q1 and Q2, and what is present at Q3 is 1, and now this is outputted. So you require in all 4 clock pulses to output the data. So are you clear about the truth table? Take a screenshot of this truth table. Okay, shall we move forward? Okay, I will clear the drawings and let us go to next configuration of shift register. Okay, so here you can observe which mode of operation. This is very simple mode of operation, that is parallel in and parallel out. So as we are using parallel in parallel out type of shift register here, and it is 4-bit shift register, we are using 4 flip-flops. So here you can observe flip-flop number 3, flip-flop number 2, flip-flop number 1 and flip-flop number 0. Okay, so this is acting as MSB. This is your MSB and this is your LSB. Okay, so now if you can see this, what you can observe, just 4 flip-flops are used. Inputs are applied separately to each D flip-flop and output is taken out separately for each flip-flop. Okay, now suppose if we apply some data over here, let us apply some data. So I'm going to apply 0, 1, 1 and 0. So here B3 is 0, B2 is 1, B1 is 1 and B0 is 1. Okay. And suppose if you apply 1 clock pulse, then what happens? Output of flip-flop 3 will become 0. Output of flip-flop number 2 will become 1. Output of flip-flop number 1 will become 1 and output of flip-flop number 0 will become 0. That means whatever you are applied at the inputs of 4 D flip-flops, the same thing you are getting at their output after application of the clock pulse. So here data will be loaded and available at the output in a single clock pulse. Okay. So parallel in, parallel out type of configuration is the fastest type of configuration, because the data is available, multiple bit data is available in only 1 clock pulse. So data is simultaneously or parallelly loaded, and therefore this is called as parallel in parallel out type of the shift register. So for this we are going to draw a truth table. So for this let me share with you a whiteboard and let us draw truth table for this. So here we can write clock. Here we can write inputs, and here we can write outputs. Okay, so here you can write D3, D2, D1 and D0. Okay, and here we will write output as Q3, Q3, Q2, Q1 and Q0. Okay, so suppose if your input is 0, 1, 1, 0, and you apply a clock pulse, in the single clock pulse output will be 0, 1, 1, 0. So whatever you apply at the input, the same thing you will get at the output. So this is what is the truth table of the parallel in parallel out type of shift register. Okay, so take a screenshot of this. Okay, so now let me again share a screen with you. So here you can observe there can be bi-directional shift register. So this bi-directional shift register is capable of shifting data either to shift it to left or to right. So in both direction it is capable of shifting the data. So such type of shift register is called as bi-directional shift register. So here what you can observe, this is a circuit diagram. This is a circuit diagram of bi-directional shift register. So here what you can observe, additional logic is used for each D flip-flop. Okay, and again this logic uses to AND gates, one OR gate. Okay, so here mode control operation is used, and this mode control M may be either 0 or 1, and accordingly your shift register will operate. And here you can observe there is input present at AND gate number 1 for right shift operation, and input present at AND gate number 8, it is used for left shift operation. Okay, so here clock is applied. Okay, so that is what you can observe in the diagram. Observe in the diagram of the bidirectional shift register. So as you can see, this type of shift register has two serial inputs, namely serial right shift data input and serial left shift data input, along with the mode control. Okay, and 4-bit bidirectional shift register, which is shown here, is having a mode control, and this mode control is responsible for controlling the mode of operation of this type of shift register. Now let us go to what happens when mode control is 1. So when mode control is 1, shift right operation will take place. Okay, and when mode control is 0, shift to left operation is carried out. Okay, so let us see what happens when m is equal to 1 and what happens when m is equal to 0. So let us see here. Now let us see when this m is equal to 1. So when m is equal to 1, upper line will be at logic 1 and lower line will be at logic 0. And as lower line will be at logic 0, one of the inputs of AND gate number 2, AND gate number 4, and AND gate number 6 and 8. All these four NAND gates, they have one of their inputs as 0. So therefore, these NAND gates are disabled. These NAND gates are disabled because its output will become 0. Its output will become 0. So here you can see output of AND gate 6 will also become 0. Output of AND gate number 8 will also become 0. That means this input is not activated here. So left shift operation is not activated here. Okay. So as this line is 0 and this line is 1, you can see AND gate number 1, one of the inputs of AND gate number 1, AND gate number 3, AND gate number 5, and AND gate number 7, they are at logic 1. That means AND gate number 1 is enabled, 3 is enabled, 5 is enabled, and 7 is enabled. Okay. So when these things are enabled, so this input D input is available here. Okay. And 0 plus D again input will be provided here. Okay. So let us call this as D3. Now here you can see this Q3 will be applied to D2 through this. So because output of this will be Q3. So 0 plus Q3 is Q3. Okay. So that means Q3 will be connected through this logic gate to D2. Similarly, Q2 will be connected through this logic gate to D1. And Q1 will be connected to D0. Okay. So as we are applying input from this side, and if we apply a clock pulse, the data will be shifted to right due to this connection. Okay. So Q3 is provided as input to Q2. That means during first clock cycle, output will be D3, D2, D1, D0. During next clock pulse, it will be X. It will be X, D3, D2, D1. Then again it will be X, X, D3, D2. Then again it will be X, 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 and that will be D3. So in this way the data will be shifted at the right when your mode control is at logic 1. Okay. हे लक्षात आलं का सगळ्यांच्या? बोला पटकन. हो किंवा नाही?
Yes, ma'am.
बर, आता पुढे जाऊ आपण. इथे हे क्लिअर करून टाकू. आता क्लिअर केल्यानंतर लेट अस सी व्हॉट हॅपन्स व्हेन युअर मोड कंट्रोल इज 0. So when mode control is 0, exactly opposite thing will happen, isn't it? So upper line will be 0 and lower line will be 1, and this 0 as it is available with gate number 1, it will be disabled. It is available with gate number 3, it is disabled. Gate number 5 is disabled. Gate number 7 is disabled. Okay. So here as 1 is applied to gate number 2, it will be enabled. Gate number 4 will be enabled, 6 will be enabled, and 8 will be enabled. Okay. Now here as you can see how the circuit goes here. So here you can observe one of the inputs of AND gate number 8 is 1, and its another input is D0. Okay. So this D0 is applied at the D input of first flip-flop. So this input is applied at the D0 flip-flop. Okay. Now what happens here? You can observe the Q0 output will be applied. Q0 output will be applied